Can you see my screen now?
Yes, I can.
Thank you very much for nice introduction. Today my topic is role of atmospheric aerosols and their potential impacts. I am Dr. Khan Alam. I am working as assistant professor in the Department of Physics, University of Peshawar. So what are aerosols? Aerosols are basically solid, liquid, gaseous particles suspended in the air. Their size varies from few nanometers to 200 of micrometers. Aerosol are further divided into different sizes. Particulate matter PM2.5, which is also called fine particles, and particulate matter PM10, which are also called coarse particles. Aerosols are further classified into natural and anthropogenic aerosols. Natural aerosols are volcanic eruptions, sea salt, mineral dust. However, anthropogenic aerosol includes industrial emission, biomass burning, vehicular emissions, domestic cooking, and other activities. In order to understand the detailed analysis of the particulate matter 10 and particulate matter 2.5, we need some characterizations technique like scanning electron microscopy that can be used to study the morphology of these particles. Aerosol vary both spatially and temporally. It can change. It has a different lifetime, varies from few hours to few weeks, depending on the particle size. There are various effects of aerosols. Some include climatic effects and some are non-climatic effects. Today's topic is regarding the climatic effect of aerosols. So I will focus on the direct effects and indirect effects of aerosols. When solar radiation is interacting with the aerosol particles, so it either scattered or it either absorbed, depend on the particle nature. If they are absorbing in nature, so they will absorb the solar radiation. If they are scattering in nature, so they will scatter the solar radiation. So consequently, they will produce warming or cooling effect. On the other side, aerosol also act as an indirect effect. Aerosol act as a cloud condensation nuclei, which help in the formation of clouds. So how can human affect clouds? Since, as I mentioned, that aerosol act as a cloud condensation nuclei, so it can modify different properties of clouds. So if the polluted, if the aerosol or pollution are mixed into the clouds, it can modify the properties of cloud. So if there are few droplet concentrations, so you will see, so the resultant cloud will be less reflective, or their albedo will be low. And if there are more droplet concentration, more polluted environment, so there will be a high reflectivity of the solar radiation. So we have a cooler climate on the Earth's surface. So while the interaction of the aerosol with the radiation, it results scattering and absorption. This process is called extension. So it comes in the direct effect. So since it depends on the aerosol nature, morphology, chemical compositions, the aerosol have different effects on the cloud properties. So if absorbing aerosols mix with the clouds, so the resulting cloud will be evaporate. So resulting, we will have no precipitations. So if there are large number of aerosol particles, so it will produce more precipitations. So by increasing the cloud droplet number concentrations, we have a large number of precipitation, and this is called the first indirect effect of aerosol or Tommy effects. Aerosol also increase the lifetime of the clouds. So if there are very small particles, very large number of particles, so it will not fall down because they are very fine and they are mixed with the clouds. So it can enhance the cloud lifetime, and it is also called the indirect effect or Albrecht effect. Furthermore, as I mentioned that in the semi-direct effect, absorbing aerosol can produce heating within the cloud. So the temperature will rise, and resulting the cloud will evaporate and we have no precipitation. When the solar radiation interact with the aerosol particles, like in the figure, a beam applied impinges on aerosol particles. So what happened? Electric charges in the particle are excited into oscillatory motion. The excited electric charges re-radiate energy in all direction, resulting scattering, and may convert a part of incident radiation into thermal energy, resulting absorptions. So light scattering mechanism of the particle can be further divided into main three categories: elastic scattering, quasi-elastic scattering, and inelastic scattering. Elastic scattering is that the incident light wavelength and the scattered light wavelength should be the same. However, in inelastic scattering, the incident light wavelength and the scattered light wavelength is not the same. So, but for aerosol radiation interaction, we are mostly talking about the elastic scattering, which is for the interaction of radiation with the aerosol is only elastic scattering is the approach which is used by the Meek theory or Meek calculation. So scattering depend on different parameters. One is the wavelength of the incident radiations. Second is the size of the scattering particles. Size of the scattering particle is basically represented by a non-dimensional parameter x, which is equal to 2 pi r by lambda, where lambda is the wavelength of the incident radiation, r is the radius of the particle. And the second parameter for scattering is the particle optical parameter, which is called the complex refractive index. Complex refractive index basically provides us about the scattering and absorption properties of the aerosol. Scattering can be further classified into main three categories: Rayleigh scattering, Mees scattering, and geometric scattering. So I'm going to introduce some of the aerosol optical properties. One of the optical properties, aerosol optical dip and angstrom exponent. Aerosol optical dip is basically the total column concentration from ground to some height, and that can be measured by the different satellite sensors. There are various satellite sensors that can provide the column concentrations. Here, beta inside the integration, beta, and then it is a height. So beta extension basically is the extension efficiency of a particle. Extension is basically when the solar radiation is passing through any layer, it results scattering and absorption. This process is called extension. On the other side, angstrom exponent is another optical parameter that can be used for the aerosol particle size indicator. So for fine particle, the angstrom exponent should be high, whereas for the large particle or dust particle, the angstrom exponent will be small. Aerosol volume size distribution is another important optical parameters that can differentiate between the column concentration of aerosols. It can say that how much bigger particle are there in the atmosphere, how much small or fine particle are there in the atmosphere. So the two mode structure shows the first one is regarding the small peak is corresponds to fine particles. Fine particles mean it is related to traffic, industrial emission, biomass burning, whereas the coarser peak corresponds to the mineral dust particles or other particles that are belongs to dust or other construction activities. Aerosol index, which is another important parameter that can distinguish between absorbing and non-absorbing aerosol. Uh, Mathematically, we say that if aerosol index is greater than 0, so it means that there are absorbing particle in the atmosphere. However, for if AI are negative or less than 0, so the scattering particle are dominants. Single scattering albedo is another important parameter that can be used for climatic effects of aerosol. To calculate the climatic effect of aerosol, single scattering albedo play a very important role. So it is basically the ratio of scattering coefficients to the total extension coefficients. It varies between 0 and 1. 0, if the value of single scattering albedo is 0, it means that there are no scattering particles, so they are totally absorbing particle. However, if the single scattering albedo reach to 1, it means that in the atmosphere only scattering particle are dominant. Remote sensing instrument, there are multiple remote sensing instrument launched by NASA and other organizations in the world. So these include some CloudSat, CALIPSO, MODIS, Sentinent, OMI, MISR. So a lot of sensors there are orbiting around the world for monitoring aerosol, for monitoring cloud properties, for monitoring vegetation, for monitoring different gases. However, we will cover some of the instrument belongs to like the ground-based instrument, Aerosol robotic network, and then we have some satellite-based instrument like MODIS, ozone monitoring instrument, and CALIPSO. So I will give a short introduction of these sensors as well. AERONET basically is a project of a federation of ground-based remote sensing aerosol network. It is established by NASA and POTONS. For the last 25 years, the AERONET provide globally observation of aerosol, optical properties, aerosol microphysical properties, uh, 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 and that can be used for research purpose, that can be used for air quality monitoring thing. So AERONET, there are 2 stations in Pakistan. One is installed in Lahore and one is installed in Karachi. Now we are also, with the help of the Lanjao University, we are installing one AERONET station here in Peshawar, in the Department of Physics, University of Peshawar. So these are some of the characteristics of AERONET. It provides us aerosol optical depth, and then it also provides different other products like inversion products and perceptible water vapor. It provides the aerosol measurement at a different wavelengths, starting from ultraviolets to mid-infrared regions. And there are different level of the data. Level 1 AERONET data belongs to the unscreened data. Level 1.5 belongs to cloud screen data. And level 2 belongs to the cloud screen and quality assured data. So the recommended data of AERONET is level 2, which is cloud screen and quality assured data. Some of the characteristics of moderate resolution imaging spectrophotometer. This instrument is installed on the Terra and Aqua satellite. It was launched in 1999 and 2002, respectively. It has a polar orbit. The Terra satellite overpass time is 10:30 in the morning, and the Aqua satellite Our pass time over Pakistan is around about 1:30 p.m. in the afternoon. At the MODES has 36 spectral bands ranging from 0.41 to 14.385 micrometers. The swath width of the MODES is it almost cover an area of 2,330 kilometers in a single shoot. And then it has some special resolutions, 250 meter, 500 meter, and 1,000 meter. For aerosol optical properties like aerosol optical depth, we have a data 3 by 3 kilometer and 10 by 10 kilometer. Models use different algorithms to retrieve aerosol properties over the land. For that purpose, dark target and deep blue algorithm is used. And then we have separate algorithm for the ocean surface. Ozone monitoring instrument has some special characteristics. It provides the information of aerosol optical properties. It also provides us some column concentration of ozone, nitrogen dioxide, sulfur dioxide, and other gases. It has a special resolution of 13 by 24 kilometer. CALIPSO is another satellite sensor. It is launched in just 16 years back. It gives us basically it gives the vertical profile of aerosol and cloud. This is the only satellite sensor that has a LiDAR, light detection and ranging. CALIPSO satellite discriminates the different aerosol type, including clean marine, dust, polluted continental, clean continental, polluted dust, and smoke particle. So CALIPSO is a very suitable satellite for classification of aerosol and for the vertical distribution of aerosol, the aerosol cloud interaction, how aerosol can modify cloud properties. So this is the best satellite because it has a LiDAR. CALIPSO, look at this picture. You can see that the CALIPSO were passed over some region in Arizona. You can see the below image shows the MODES were passed over that specific time that have this CALIPSO image. So you can see that from the below image, the more you can see a fire, and then you can also see with the CALIPSO vertical profile that that the smoke flume can reach up to 5 kilometers and an altitude of 5 kilometers. So CALIPSO can also be used for the validation of MODES product. So I'm going to discuss some of the case studies regarding the dust and the smoke. So the first is belong to dust characteristics over the Middle East and South Asia. So look at this image. Actually, this is a dust storm occurred in Iraq, and the Middle East. So normally this region, Iraq, Saudi Arabia, and the Persian Gulf form a hotspot region that has reported the highest occurrence of dust storm. So in March 2012, two separate dust storms created. One is Iraq, and then due to the high low pressure gradient, this dust storm shifted towards Saudi Arabia, and then it comes to the Red Sea, and then it goes towards Pakistan. And then there is another dust storm in the south western region of Pakistan on the second day of the first dust storm, and this dust storm also goes towards Pakistan, and it reached to Lahore. So the line shows the red line shows, and these are some of the back trajectory that how this dust storm transported from this Middle East regions to Pakistan region to Lahore. These are some of the dust images detected by MODES sensor. You see that this dust is occur in this over the Arabian Sea in the southern region of Pakistan, and then this dust storm is easily transported to thousands of kilometers from these regions towards Pakistan, and it covers the whole region. That reduce the air quality in the region, and also it affects the radiation budget, and resulting it produce the warming effect in the tropospheric layer. So during this dust storm, we have analyze aerosol optical dip. Aerosol optical, as I mentioned previously, aerosol optical dip is the vertical column concentration from the ground to some height. So in this Middle East region, you can see this first figure. The aerosol optical dip is very high. It goes to 4.5 over the Saudi Arabia region, and also at Bahrain, at Doha, at Kuwait, and at Arabian Sea, and Chabahar, which is the city of Iran, Muscat, and Lahore, Pakistan. So, so by showing these figures, that it shows that this is not regional; it is a global. It is covered the whole region of Southeast Asia, and it covers many countries like Middle East, Iran, Pakistan, India, and affected the visibility and the air quality in these regions. This is the CALIPSO vertical profile from on the same dusty days. So we see that, like, if you look at this yellow color, it corresponds to paver dust. So in the whole region, like it starts from latitude of 37.919 to almost 19 to 17 latitude, and longitude from 74 to 69. This region belongs to this Middle East and Pakistan. So we see that this dust is if you look at this dust is vertically distributed from 2 kilometers to, and it reached up to 10 kilometers in some places, but at 5 kilometers in some other places. This is the volume size distribution during these dusty days. So you see that the fine mode, particle is very small as compared to the coarse mode. So it means that the dust particles, the coarse particle during these days are dominated by the fine particle. So we have a large contrasting variation of the fine and coarse mode particles, and this is also an indication of the ground, the AERONET retrieval show that the dust particles are dominant as compared to the fine particles during these days. Single scattering albedo also provide us about the scattering and absorption information. During the dusty days, we see that the single scattering albedo reached to 1. It means that the short wave radiation is totally scattered by the dust particles. So we have around about 0.99, the single scattering albedo reached to 0.99. It also represented the coarse particle is responsible for the scattering of solar radiation. This is the aerosol transport from Middle East and from Syria, from Iraq regions to Lahore. So so we use high split model. So these are some results of high split model on the same dusty days, and it is clearly see that the air masses is reaching towards Lahore from this Middle East and from this Saudi Arabia and from Red Sea, and these air masses carries dust particles, and these dust particles can easily reach to Lahore. So another case study is regarding the smoke characteristics over the Himalaya regions. In this figure, we see a thick smoke which is spread over this whole region, where the dot spot indicate that these are the hot spot region from where the smoke is created. So this region is nearby Lahore, and this region is agricultural land of India, where the farmer normally grow rice, and after harvesting the rice, they burn the residue. So that's why the smoke is created, and it spread thousands of kilometers from this region, and it covers the major part of Pakistan, particularly Punjab, and also it spreads in the northern eastern part of India as well. This is another evidence of smoke in this Himalaya regions. So we see that again we see these hotspot, red hotspot detected by the model sensor, where the temperature is high. So these spots corresponded. There is some burning activity, some firing activities, and resulting a huge haze or smoke in the region, which badly affect the air quality, particularly in Punjab and also in some part of northern Pakistan. This is the aerosol optical depth variation during the biomass burning episode. So if you look at the aerosol optical depth values reach above 4, and which show that the aerosol column concentration is very high. So if we look at the second figure, so we see that there is some fine particles and there are some coarse particles. So the total aerosol optical depth is 2.752, but the fine particle is 2.677. So it means that the fine particle concentration are dominant, whereas we see that the coarse particles is only the thickness, the aerosol optical thickness or aerosol optical depth of the coarse particle is only 0.075. So during this biomass burning episode, as it's belong to fine particles, so we have higher concentration of aerosol optical dip of fine particles. So it can also, this optical dip also provide you the indication of fine and coarse particle as well. So during this hazy days, smoky days, we also see that the volume concentration of fine particle is higher than the coarse particle. This is also reflecting that the fine particle concentration during the smoke event is dominant over the other particles like mineral dust or resuspended dust or other coarse particles. This optical parameter, single scattering albedo, this is for both dust and haze, and you look at the contrasting effect of haze and dust. So single scattering albedo is decreasing with the wavelength of the smoke particle. It means that absorption is taking place. However, for dust particle, the single scattering albedo is increasing, which shows that the scattering of the aerosol particle is taking place. So furthermore, the aerosol can be classified by aerosol optical properties like aerosol optical dip and angstrom exponent. So if we make a scatter plot or if we do some cluster analysis, then we can separate dust particle from biomass burning in urban industrial, and if there are some mixed particles, so we can easily do this by AOD and AE analysis. So this is again the previous page, but on this side we see that over Lahore, in this smoky days, we have a higher concentration of the fine particle as compared to the coarse particle. And similarly, over this Kanpur, which is a city in India, we have higher concentration of fine particle as compared to coarse particles. That means that the smoke particles in this region are dominant during this time period. This is the volume size distribution during the dusty days. You see that the circle belong, and the dusty images, there is a circle. This area is belong to Lahore, the AERONET site in Lahore, and we see that we have a highest concentration of the coarse particles during these dusty days. So aerosol can further be classified by angstrom exponent and aerosol index that can provide us much better information of dusty and non-dusty or mixed particles. So aerosol types were identified as mostly dusty, mostly black carbon, mixed BC, and dust particles. So for that, we define a threshold that if the angstrom exponent is less than if the angstrom exponent lies between 0.4 and 0, however, the AI, the aerosol index, lies between 5 and 1.57. So it corresponds to dust particles. If the angstrom exponent lies between 1.5 to 0.92, and the aerosol index lie between 1.52 to 2.44, so it corresponds to black carbon particles. And if the angstrom exponent corresponds to 1, between 0 and 1, and the aerosol index is between 0.5 to 1.55, so it means that mixed particles, mixed dust and black carbon particle are dominant. We also use the vertical distribution of CALIPSO, which also provide us the classification of aerosol, the total attenuated backscattering, provide us that there are that the smoke particle, the dust particle are dominant during the dusty days. The depolarization ratio also provide the information that the fine particle are dominant. And if you look at the aerosol subtype classification, so the yellow curve corresponds to the dust particle, so it belongs to dusty days. So based on the CALIPSO vertical profile, we can also differentiate between different nature of particles. We can classify aerosol into major types. This is another CALIPSO profile. Again, this shows that we have some mixed type of particles, which include smoke particles, and also we have some dust polluted particles, and some dust particles are dominated over our study regions. Now, in the last, I will discuss aerosol impacts on the climates. So the aerosol impacts is basically calculated when the solar radiation is interacting with the aerosol particles. So for this purpose, we need to calculate the radiative effect of the aerosol or aerosol radiative effect. So which is aerosol, basically aerosol radiative effect is the difference between the down and up fluxes for both with and without aerosols. So you need to calculate the down and up fluxes in the clean environment, and you need to calculate the down and upward fluxes of the solar radiation in the polluted environment. And then you can use some model which is called in the next slide I will show you that how we can calculate these fluxes. And then so we need to calculate the top of the atmospheric fluxes, and we also need to calculate the fluxes at the Earth's surface, and then we also need to calculate the fluxes within the atmosphere. And finally, we need to calculate the atmospheric heating rate, how much heat is produced by the absorption or scattering of the solar radiations. So we use a model which is called Santa Barbara Discard Atmospheric Radiative Transfer Model for the calculation of the radiative effects, for the calculation of solar fluxes. So the main input parameters to this model are aerosol optical depth, single scattering albedo, asymmetry parameter, water vapor, and then we need some data from MODES, the surface albedo, and then some columnar ozone concentration, which is obtained from the OMI. And then we calculate the short direct aerosol radiative forcing at the top of the atmosphere, and then at the surface of the Earth, and then within the atmosphere. And finally, we calculate the atmospheric heating rate. So these are the results. Look at here. So we see that at the top of the atmosphere and at the surface, we have a very strong negative atmospheric forcing, and particularly on 21st July 2012, we have very strong negative surface forcing, and then, but once we subtract the surface forcing from the top of the atmospheric forcing, then we calculate the atmospheric forcing, which is positive, and which is 60, which reached to 60 watt per minute. And the bracket 2.2 is corresponds to the heating rate, which is calculated Kelvin per day. So the positive forcing for these biomass burning or smoky days and for the dusty days are calculated. So we see that the dust produce cooling effect both at the top of the atmosphere and the Earth's surface as well. However, it produces warming effect within the atmosphere. Overall, both smoke and dust particle produce heating effect within the atmosphere. So we also calculated the long wave. This was for the short wave radiation fluxes. We also calculated the long wave radiative fluxes during the dust episode, during the dusty period, and we see that the long wave fluxes both at the top of the atmosphere and on the surface produce warming effect. However, on the surface and TOA, the short wave radiative forcing produce cooling effect. In summary, aerosol, remote sensing, satellite sensor or ground station play an important role in monitoring the spatial temporal and synoptic characteristics of aerosol, their impacts on air quality and climate change. Aerosol characteristics, including their optical and radiative properties, have been analyzed during dust and haze episode over the Middle East and Southeast Asia using modest AERONET observations. We also use some of the data from the highest plate and some of the CALIPSO observation as well. And we see that the aerosol optical tip concentration were higher during the dust episode over this region. These are some of the conclusions. So normally the optical properties of aerosol like volume size distribution and single scattering albedo provide very detailed information about the dust, and the biomass aerosol or the smoke particle aerosol, and we see that during the dust time period, the dust is dominant over the urban industrial aerosols. So we have maximum AOD during the hazy days as well. And from the optical properties, volume size distribution and single scattering albedo, we concluded that the haze particle, the smoke particles during the hazy days is dominant over the other aerosol particles. And the heating rate during dust was 2.50 and during the haze it was 3.30. Overall, as I mentioned, that both dust and haze produce warming effect within the atmosphere. However, it produces cooling effect on the top of the atmosphere as well as on the Earth's surface. So now we are establishing an atmospheric physics laboratory, atmospheric and environmental research laboratory with the support of Blanche University. So in future, we will have a wide range of ground sensor data like Lidar, and in Sunphotometer, we are installing Sunphotometer and Lidar at Peshawar, and we have some spectrometer which will provide us some temperature profile, high volume sampler which will provide us some PM10 and PM2.5 profile, and then we have some automatic weather station which will provide us the meteorological parameter. And also we have ethylometer optical instrument which is used to calculate the black carbon concentration. So in near future, we will have a huge number of instruments that can be used for regular aerosol monitoring that can address the air quality, human health issue, and the climatic implication over this region. Thank you very much.
Thank you, Dr. Sab, for your very insightful presentation indeed. So now we still have 6-7 minutes for the question and answer session, please. So raise your hand if you have any question. Any question from the audience, please? Yes, so we have a question from Ms. Kainat Javed. Please go ahead.
Thank you so much, sir. This presentation was quite like professional kind of, but being a little, I know a little about it. So I want to know that when we are using any instrument to measure some parameter, for example, an aerosol, so how can we go for specificity? Like, how can we go for a specific aerosol? Like, we can see that there are lots of pollutants in the environment. So how can we go for like specialization? And second thing is that does your university collaborate with other universities when it comes to sharing the instruments? Thank you.
Thank you very much for your questions. Regarding your first question, like it depends on what you want to measure. Like if you are going to measure particulate matter, either PM10 or PM2.5, And then what you get some sample, collected sample from any location. So then you need to do some characterization of that particulates. If you are interested in and source apportionment, so then you need to do some ICP-MS analysis, inductive coupled plasma atomic mass spectroscopy analysis. If you are interested in the morphology or the size composition, then you need to do scanning electron microscopy or EDX analysis. And if you are interested in the nature, the bonds, the bond strength between the elements that are in the sample, then you need to do some Fourier transform infrared spectroscopy analysis, which is called FTIR analysis. So it is up to you. If you have optical sensor, like for example, you have athylometer. So athylometer basically use some algorithms. It is optical sensor, but it can be used to calculate the concentration of black carbon. And then you can also use some other instrument for that specific purpose. So it is the like totally it correspond on on the requirement what you want to measure. And regarding your second questions, there are some instruments that can be borrowed to or that can be used in collaboration purpose. But there are some instruments they are fixed install. Like for example, Lidar, which is a very heavy instrument. It has a weight of 200 more than 200 kg. So it's not possible to carry this instrument from one place to another place. But there are some mobile instrument that can be used to carry from one place to another place. So, and yes, we are open for collaborations. And I have collaboration with Professor Fahim as well. We are sharing data as well. We are working together. We are working in manuscript together. So I welcome all. If anyone want to collaborate with us, so you are most welcome.
Thank you,
Thank you
Dr.
so much.
Yeah. So any other question? Dr. Asif, please proceed.
Yes, so thank you very much, Dr. Fahim. And since nobody else is asking a question, so I thought I should take liberty to ask a question. But before I ask a question, I just have a couple of comments. And thank you very much, Dr. Khan, for such a splendid presentation in terms of the optical measurements particularly. So the comment which I actually have is related to scattering. And as you explained in your presentation, it's a phenomenon that occurs when the solar radiation passes through the air and some of the wavelengths are deflected randomly in all directions when they strike against the suspended particles or aerosols. So the change of direction is, of the radiation, it occurs randomly. So the only comment which I would like to make is that the amount and the direction of scatter, it depends on the ratio of the radius of the scattering particle to the wavelength of the energy. And I think that is something that is also considered in these observations as well, which you presented in your presentation. Secondly, can you please bring up the slide where you showed data about the black carbon? Yes, that's
This one?
wonderful. So, yes, that's one. So another comment is that a very interesting finding in this is the difference in the weathers. For example, if you look at the summer season and compare that with the winter season, then we can see the difference of the aerosols that are present in the atmosphere in the region that you have investigated. So I suppose when you talk about the pre-monsoon season. Obviously, the monsoon, these are winds which blow. They can be either dry winds or they can be wet winds. The wet winds, they bring in a lot of rain during the monsoon season. The dry winds, they do not bring in a lot of rain. So I suppose when the dust particle is moving, then that is mainly due to the dry winds which are moving throughout the region. And the comment with regards to the winter concentration of black carbon is because in the winter we have accumulation of these pollutants region-wise, and that's why I suppose you can see the increased concentration of black carbon in the post-monsoon season, particularly when it is the winter season. So I suppose that that's something which is going on in this data.
Thank you very much for your question, Dr. Asif. If you look at this figure, we see that in winter we have a higher concentration of the black carbon. Actually, during the winter time, if we look at the meteorological parameter, like we have very low winds, the winds are almost calm, they are stagnant. So we have only the local sources of aerosol, like from industrial emissions, from vehicular emissions, and maybe from some domestic purposes. We burn wood for cooking purposes as well. And so that's why we have a black carbon concentration in the winter. However, during the other seasons, there are some mixed scenario. So we have some long range transported aerosol as well. Also, if there are some soil, like we know that in Pakistan, we have barren surfaces. The surfaces are not concrete properly, so we have loose material on the surface, on roads, on footpath. So that loose material belongs to the dust, and due to the heating in spring and summer, so that loose material is heated up, and by winds it goes up in the atmosphere. So that's why we see in the pre-monsoon and also in the monsoon period, we have some concentration of dust particle as well as some black carbon or industrial emission particles.
Yes, yes, thank you very much for that. And as I said, there's accumulation of these pollutants, particularly in the winter season, which you have also explained. And the question which I actually have is related to slide number 45. So if you can please bring that up, where you were talking about the reflectivity based on this one. So when we talk about the polluted atmosphere and the clean atmosphere, I suppose this is also based on the perspective. For example, we can have pollutants where we have, for example, nitrates that have high reflectivity as compared to black carbon, which will absorb more of the solar radiation. So in this case, I suppose it also depends on the nature of the pollutant. So we know that ammonia is one of the precursors of the atmospheric nitrates, which are present in the atmosphere. They usually bounded to particulate matter, and they can be considered as secondary aerosols. So does it really depend on the nature of the pollutant, whether the sun rays they're being reflected or whether they're being absorbed in that particular region of the atmosphere? Thank you.
Yes, you are right. The interaction of the radiation with the particles depend on the particle nature. Since we are talking about the total column concentration, so in that total column concentration, we have mixed particle, we have dust particle, we have black carbon, we have some other sulfate particles, we have some iron particle, and we have some sulfur particle. But we did not individually calculate the interaction of radiation with these particles. For that purpose, then we need to collect the particulate metadata, or we can use some other sensor there, and then we find out the optical properties of individual particle, like for black carbon, for sulfur particles, for dust particle. Then individually we calculate the radiative forcing, then definitely we will get a different scenario. So, but here in this case, since we are collecting, we have a ground sensor AERONET. So AERONET, and which can measure the total column concentration of the particle. So, but in future, like with other instrument like Lidar, like Ethylometer, like other instrument that can be used for a particular pollution for a target pollution like for black carbon or for mineral dust, then we can separately calculate the optical properties and the radiative properties and their climatic implication as well.
Yes, so thank you very much for that response. And just a quick point, the reason why I asked that question is because recently there was a study which was published in Nature Geoscience, and this is actually related to the control of particulate nitrate air pollution in China, where because we know that in the last few years the air quality has increased in China, but the nitrate air pollution, it continued to deteriorate the air quality. And they've actually come up with this idea that, well, their results actually, they suggest that decreasing the ammonia emissions would decrease particulate nitrate, which is actually considered as a pollutant, and then it can affect the reflectivity. So just want you to bring that up to the participants. Thank you.
In the interest of the time, if I can request, we're going to meet tomorrow at 10 o'clock again. So if there is any quick questions, Dr. Fahim, we'll ask. Otherwise, I have one question to ask the participant in the last.
Okay, so I guess if there's no technical question from the audience, then I guess we're done for today's session.
All right. So I just you all see something on your screen? Just yes or no questions. Please write it so please we can see how well we are doing so far. I'll stop the recording. Should not be part of the recording.